This is slide number 54 and I am your presenter Asloob Mudassar. Today we are going to talk about the image formation with a thin convex lens. So let's look at the geometry that we are using. You see that there are three planes: zeta eta plane, xy plane, uv plane. The zeta eta plane is the input object plane. The convex lens, the thin convex lens, is placed at the xy plane, and the image plane is the UV plane. All these planes are piercing z-axis perpendicularly. The separation between the input object plane and the thin convex lens plane is denoted by capital Z1, and the distance between the lens and the image plane is by distance Z2. So optic axis is also passing along the z-axis, and you know that all these three planes are centered at the optic axis. And the imaging system based on the thin aberration-free convex lens is shown. So what is the problem? The problem is that we want to calculate, there is an object, for example, at the input plane, that is for example a point source, or generally a field is known at the zeta eta plane, and we want to calculate the field at the UV plane, that is at the image plane. And of course the field will pass through this thin convex lens and will focus the information at the image plane. So any information, for example a point source existing at an input object or some field existing at the input object, will pass through the thin convex lens and then will contribute at the image plane. And so we shall have to find out the field at the image plane in terms of the field at the input object plane. So let's read some statements. Thin convex lens of a focal length f. We are using a thin convex lens of a focal length f, and the region we are considering for the lens is isoplanatic region, or the paraxial region of the lens. We have already explained isoplanatic terms in many times in previous slides. Illumination is coherent, and under that condition the system is linear in amplitude. So this our system is working, we are illuminating it coherently, so this system is linear in amplitude. The object, the lens and the image are located at the planes designated by zeta eta, xy, uv plane respectively, and all the planes are parallel to each other and perpendicular to z-axis. For a real image, z1 must be greater than f. That is, the image should lie, that is, the image plane should lie beyond the distance z1, which is greater than the focal length of this lens, and z2 is greater than or equal to f. So these are the two conditions for the imaging scenario. The distance z2 must satisfy the geometrical optics imaging equation given below. So you see that our system, our imaging equation for this system under the geometrical optics will be 1 over z1 plus 1 over z2 is equal to 1 over f. So here z1 is the object distance, z2 is the image plane distance, and f is the focal length of the lens. So this is equation number 59. Assume that the object is illuminated by a coherent beam such that the field just after the object is u0 of zeta comma eta. So this is the field just after the object, which we have denoted as u0 as a function of zeta and eta, and the field at the image plane is ui of u comma v. So this is the image plane field, this is the object plane field. These two plane fields, we have to find out a relationship between them. The system is linear in a complex field. The two fields can be related through the superposition integral defined below. So in equation number 60, we have the relationship between these two fields, that is the input field u0 as a function of zeta and eta, and the output field is ui of u and v through this superposition integral. And you know that there is one term which is kappa. Kappa is present, and the kappa has coordinate uv semicolon with zeta and eta. So actually kappa is connecting some information from zeta eta plane to the uv plane. So this is the superposition integral. Now you know that if we set for example, if we look at below the equation number 60, we have set, if we set kappa is equal to delta of u minus zeta v minus eta in the integral, then you know that this delta will be 0 only when u is equal to zeta, v is equal to zeta, and the integral you know that will vanish out, giving you the answer at u naught of zeta and eta. And you see that then you have the input field ui of u v is approximately equal to u naught of zeta and eta. Solve the integral when kappa attains this value, that is kappa is a point source or point image. So if kappa is a point image, then you know that the two fields will be identical to each other. So you see that here if then the two fields will be identical to each other. If ui of u comma v is a magnified or demagnified version of u naught of zeta comma eta by a factor m, then kappa of u comma v semicolon zeta comma eta can be related to the Dirac delta function through the relationship. So we have kappa of u comma v semicolon zeta comma eta is equal to a times delta of u plus minus m times zeta and v plus minus m times eta. Look at the expression of a kappa under equation number 16, in which we have set kappa is equal to delta of u minus zeta comma v minus eta. Then you know that under this condition we see that the input that the field at the image plane is equal to the field at the object plane, and this is the field when we calculated under the condition that the imaging system has a unit magnification. But you know that if the system has some magnification, then we over kappa will is equal to as given in equation number 61, that is kappa of u comma v semicolon zeta comma eta is equal to a times into delta of u plus minus m times zeta and v plus minus m times eta. So you see that m is the magnification of the system and a is the magnitude of this delta function, or a could be real or a could be complex. So this is given in equation number 61. Kappa is referred to as the impulse response of the system, because the delta is an impulse response. You know that it is impulse, so kappa is referred to as the impulse response of the system. Plus minus sign takes care of the inversion property of the lens through u plus minus m times zeta is equal to 0 and v plus minus m times eta is equal to 0, or u is equal to minus plus m times zeta, or v is equal to minus plus m times eta. A is generally a complex constant which not only determines the magnitude of the delta function but also injects any phase variation through the system. So you see that here kappa is actually the impulse response of the system. That is impulse. What is the impulse response? Is mean that we have at the input an impulse that is a point source or a delta function, and then we get an image of that one which is referred to as the impulse response of the system. That is what is the response of the system under an impulse, that is called impulse response, or we can also regard this as the point spread function. So we can write you know that for a system with m magnification, system having a magnification equal to m, we have used the previous equation, for example equation number 60, and we have plugged in there the value of a kappa, assuming that the system has m times the magnification. So we have, you see that in the integral we have the input field, we have the field at the image plane as a function of uv at the left hand side, and the integral contains the u naught, the field at the object plane, and then you know that we have a times delta of u plus minus m times zeta and v plus minus m times eta. This is the delta function we have there as because we are assuming that the value of kappa is this. So you see that the solving this integral we will get a, that is the magnitude of the delta function, and then you know that the integral will be solved as u naught of minus plus u over m comma minus plus v over m, where we have used zeta is equal to minus plus u over m and eta is equal to minus plus v over m to set the coordinates or the arguments of the delta functions equal to 0 and 0 in order to solve this integral. We have used these values of zeta and eta as we have just read in equation number 52 to obtain that the image plane field will be equal to a times the object field plane at the coordinates of minus plus u over m comma minus plus v over m. Now let's consider the object field object field consists of a point source located at zeta naught and eta naught, which can be represented by a delta function u naught of zeta and eta is equal to delta of zeta minus zeta naught comma eta minus eta naught. So here you see that we are assuming that our input field is a point source, is a delta function located at the coordinates zeta and eta, zeta naught and eta naught, as we have shown in equation number 63 in the integral. So substituting the value of there, the input field equal to delta of zeta minus eta and delta of zeta minus zeta naught and eta minus eta naught as a point source located at the location of zeta naught and eta naught in the input plane, then you know that solving this integral we have a kappa. We have the field which we have the field at the image plane, which is equal to kappa times of u comma v semicolon with zeta naught and eta naught. So from equation number 63 we follow that kappa as a function of u comma v semicolon zeta naught minus eta naught is actually the field at the image plane, as obvious from the left hand side. This is the field at the image plane at the coordinates u comma v due to the input source located at the object plane at the coordinates zeta naught and eta naught. So kappa of u comma v semicolon zeta naught and eta naught is thus the image at the uv plane due to the point source located at zeta naught and eta naught. So kappa of u comma v semicolon zeta naught and eta naught is the response of the system to a point source, that is the impulse, and is thus named as the impulse response of the system or the point spread function of the system. So remember that the impulse response or the point spread function are actually the image of the imaging system at the image of the imaging system due to a point source located at the object plane. So let's carry out the mathematical expression for kappa of u comma v semicolon with zeta naught and eta naught, which means that a point source zeta naught and eta naught is placed at the input object plane, and we want to find out the field at the uv plane. So then the field at the uv plane will be regarded as kappa, as we have calculated in over here in equation number 69. Now we are going to calculate a detailed expression for that one. The field just before the lens represented by ul of x comma y due to the point source located at zeta naught and eta naught at a distance z1 can be found using the Fresnel diffraction formula. So you see that we are going to apply the Fresnel diffraction formula because we are assuming that the field just after this object is known and which was regarded as ul of zeta and eta, and we want to make this field to travel a distance z1 to reach at the xy plane. So in this region, that is in the region where we have the distance z1, we want to apply the Fresnel formula to calculate the field from the field just after this input object and the field just before the lens. So let's calculate that one. So this is given by equation number 64. The field just before the lens represented by ul of x comma y due to the point source located at zeta naught and eta naught at a distance z1 can be found using Fresnel diffraction formula, which is given. So you know that in the Fresnel diffraction formula, if you look, we have the distance there as z1. All the where you can see that we have z1 over there. It means that we are calculating the field at after a distance z1, and you know that input field is delta of zeta minus zeta naught comma eta minus eta naught. This is our input field, and the rest of the quantities are the expressions available in the Fresnel integral formula. So if we solve this integral, that is if you set zeta is equal to zeta naught in the delta function and eta is equal to eta naught in the delta function, to set its argument value is equal to 0, so that the integral at these particular value, when you assign the particular values to the integral will vanish out, and you will get the second row in the equation number 64, which is e to the power iota k z1 over iota lambda z1 into e to the power iota k over 2 z1, and within the curly bracket we have x minus zeta naught square plus y minus eta naught square. So you see that this is the field that we have calculated just before the lens, and you know that the field just after the lens will be equal to the input field multiplied by the pupil function of lens, which is p of x comma y, multiplied by phase transmittance function of the lens, which is equal to e to the power minus iota k over 2f, and within the bracket we have x square plus y square, and on the right hand side we have the input field, which is input on the lens, which is ul of x comma y, and on the right hand side, which is ul prime x comma y, is actually the output field or the field just after the lens. So equation number 65 gives you the field just after the lens. Okay, the image plane is located at a distance z2 from the lens, and the field there is designated by kappa of u comma v semicolon zeta naught and eta naught, and is found from the Fresnel diffraction formula. So what we are now going to do is that we have calculated the field just after the lens, and the field named was ul prime. Then you know that we want this field ul prime to travel a distance z2 to reach the image plane where the field we have assumed is kappa. So you see that we have to apply the Fresnel diffraction formula for the region where the distance z2 has been defined. So applying that one, and that is the Fresnel diffraction formula. For the distance z2. Now you see that we are here in the formula in equation number 66 we have an involvement of the parameter z2 over here. In the previous equation, when we calculated the parameter before the lens, that is the field before the lens, then the distance was z1. There we used z1 in the Fresnel diffraction formula. Now we are using z2 because we are calculating the field behind the lens and in the region where the distance z2 was defined, and the Fresnel field is given by equation number 66. So you see that you can have the field at the image plane, which is kappa of u comma v semicolon zeta naught and eta naught, and on the right hand side we have applied the Fresnel diffraction formula, and you know that in the integral we have ul prime, which was the field just after the lens, and now due to this formula this field will propagate to the image plane, which is where the image plane is located at the coordinates u comma v. So you know that here we have the field we have here is ul prime, which is which we have shown in figure number which we have shown in equation number 65. So from the equation number 65 we are going to plug in the value of this field over there, so that we can calculate equation number this field, that is we can calculate this field. So you see that before calculating the field ul prime, what we need to and to substitute that one in equation number 66, we want to calculate this ul prime in equation number 61 by substituting ul as a function of xy from equation number 64. So we are going to use equation number 64 in equation number 65 on the right hand side to replace the field ul of x comma y, so that we can have a detailed expression of ul prime as a function of x comma y, and then later on we shall use this field in the formula in equation number 66. So first now what we are going to do is that we are going to use equation number 64 in equation number 65, and the result is shown. So you see that the terms that we have substituted are shown in red, and the original terms that were present in this formula is in black. So you see that the original terms that are present in this formula in equation number 65 are in black, and these terms that we substitute from equation number 64 will be shown in red. So you see that this is the expression that we have shown, and you know that we have combined these terms. For example, we have if you look at this one, we have combined some terms in the integral. We have combined these terms. For example, e to the power iota k over 2 multiplied within the parenthesis 1 over z1 minus 1 over f multiplied by x square plus y square. So this is the exponent that is combining two terms, 1 over z1 and 1 over f, and you know that we have zeta naught square plus eta naught square, and we have some other terms which are the product terms. For example, x into zeta naught plus y into eta naught, as obvious in the second row of equation number 67. So you see that we have now simplified the field just after the lens. Now we are going to plug in this field in equation number 66 so that we can calculate kappa on the left hand side of equation number 66 in terms of the input parameters. So you see that now we are going to substitute these values in equation number 66. But you know that in the 66, first before we make the substitution of ul prime as a function of x comma y, what we want to do is that we want to expand the exponential, that is e to the power iota k over 2 z2, and within the curly bracket we have u minus x whole square plus v minus y whole square. We want to expand this one, and then we want to attain the expanded form of equation number 67 over here. So here we have the expanded form of equation number 67 in front of us, where we expanded the this exponential factor. So you can see that we have the terms, quadratic terms in uv plane, we have the quadratic terms in the xy plane, and we have some product terms which are x into u and y into v. These terms are present. So you know that now we are able to substitute the value of ul prime from equation number 67 into this formula, so that we can calculate the detailed information, the detailed expression for the kappa. So doing that one, we have labeled in red the substitutions that we have made. For example, we have replaced ul prime of x comma y from equation number 67, and we have replaced them in red form so that we can make the difference between the substituted values and the other values. So you see that you can see that a large number of exponents are present, but some of we have combined. For example, we can combine some of the exponents, and if you look at the second row in the integral, for example, within the integral we have combined the three terms as e to the power iota k over 2, and within the parentheses we have 1 over z1 plus 1 over z2 minus 1 over f, and outside we have x square plus y square. And similarly we have combined the other terms. For example, we have also some terms within the integral. For example, e to the power minus iota over k, within the curly bracket we have u naught over zeta z1 plus u over z2, and this whole bracket is multiplied by x plus eta naught over z1 plus v over z2. This whole bracket is multiplied by y, and you know that since the x and y are the variables of the integral, so this term is kept within the integral. The other terms which are not the functions of x, y, we have taken them outside the integral, as you can see in this in the second step of equation number 64. So here we have kappa, we have calculated the detailed expression of the kappa. Now we want to set some modifications over here, or we can set some suggestions for the equation number 68. For example, if 1 over z1 plus 1 over z2 minus 1 over f is greater than 0, for example, this expression that we are talking about over here within the integral, if this expression is greater than 0, then kappa will be focused after the uv plane. And if 1 over z1 plus 1 over z2 minus 1 over f is less than 0, then kappa will be focused before the uv plane. And if 1 over z1 plus 1 over z2 minus 1 over f is equal to 0, then kappa will be focused sharply on the uv plane. So you know that since we want that the kappa should be sharp, that is our image should be sharp, we want to use the third value, that is 1 over z1 plus 1 over z2 minus 1 over f is equal to 0. We want to set this one in this integral 64. Then you know that this term which is containing a quadratic phase factor in x square plus y square will be vanish out from the integral. Okay, so 1 over z1 plus 1 over z2 minus 1 over f is equal to 0 is the classical So this is the classical lens law or geometrical optics lens law. for sharply focused kappa of u comma v semicolon z naught, zeta naught minus eta naught, the expression takes the form. So you know that now in equation number 69 we are giving the expression for the kappa which gives the value of the kappa for a sharply focused kappa. So then you see that we have some terms which are outside the integrals, not depending upon the x y variables, and there are some terms within the integral sign which are depending upon the x and y parameters. So now we want to write equation number 69 in a more meaningful form, that is, let's express this equation in the Fourier transform integral. So let's represent this integral in a meaningful form, that is in the Fourier transform. So you see that I have introduced over here in equation for the equation number 69, I have introduced n for all the terms which are not depending upon the integral. So capital N is denoting all those terms which we are going to explain later on. And then you know that within the integral we have in the curly bracket p of xy multiplied by e to the power minus iota 2 pi zeta naught prime into x plus eta naught prime into y. And then outside the integral we have the parameter of the Fourier transform integral, that is e to the power minus iota 2 pi u prime x plus v prime y, and then we have the variables of the integral, that is dx and dy, as in equation number 70. So you see that we have made the modifications and we have introduced zeta naught prime, eta naught prime, and similarly we have introduced u prime and v prime. These terms are explained below, and you know that this integral now look like, that is, we are actually calculating the Fourier transform of the terms within the curly bracket. So this integral in equation number 70 is going to give you the Fourier transform of the integral within the curly bracket, subject to the variables which we have the modified variables, or you can say that the scaled variables, that is the n variable, zeta naught prime, eta naught prime, u prime and v prime. These variables are explained next. So ignoring n, the quadratic phase factors and the scaling of constants, impulse response is found to be proportional to the Fourier transform of the lens phase modified people function. So you see that p of x comma y is the lens people function, and you know that this is multiplied by with some phase term. So we can regard this as the lens phase modified people function. So this is the Fourier transform of the lens phase modified people function. In writing equation number 70, we have introduced following scaling of coordinates which are given next. So zeta naught prime was equal to zeta naught over lambda z1, eta naught prime was equal to eta naught over lambda z1, u prime is equal to u over lambda z2, v prime is equal to v over lambda z2, and then n was defined equal to e to the power iota k multiplied by z1 plus z2 divided by iota square lambda square z1 and z2, and then two quadratic phase vector. One is the related with the input object, so e to the power iota k over 2 z1 into zeta naught square plus eta naught square, and the other term is the quadratic phase term related with the output plane. So we have e to the power iota k over 2 z2 multiplied by u square plus v square, as in equation number 71 and 72 respectively. We have defined all these scaled variables. So let's write equation number 70, that is this one, in some more meaningful form, as we are giving in equation number 73. So kappa is now is equal to n times the Fourier transform of this quantity, and this quantity you know that we have regarded it as the lens phase modified people function. So it is the Fourier transform of the lens phase modified people function. So you see that the Fourier transform of these two quantities is equal to the Fourier transform of first quantity convolved with the Fourier transform of the second quantity, because the convolution sign is there and we have applied the convolution theorem. So the Fourier transform of p of xy has been denoted by capital pi of u prime comma v prime, because u prime and v prime are the variables at the output plane, which we have are also in the scaled form of the variables at the output plane or the image plane, and then you know that we have convolved it with delta of the Fourier transform of this exponent form, that is e to the power minus iota 2 pi zeta naught prime into x plus eta naught prime y is given in terms of the delta function, that is the delta of u prime plus zeta naught prime comma v prime plus eta naught prime. So this delta function is the Fourier transform of the term in the exponent in the curly brackets shown above. So you know that here we convolve pi of u prime comma v prime with the delta function. So what will happen, that the u prime and v prime contained in the function pi will be replaced by the arguments of the delta function. So the next step is n times pi fourth step is n times pi, and pi contains the arguments u prime plus zeta naught prime comma v prime plus eta naught prime. So we are using the original variables, that is we are original variables as shown in equation number 75. We are using those variables, and then you know that the last step of equation number 73 becomes equal to, that is the input field, that is the kappa, that is the field at the image plane, that is will given. So this kappa is the sharply focused image plane, is given by n times multiplied by the pi as a function of u over lambda z naught plus zeta naught over lambda z1 comma v over lambda z2 plus eta over lambda z1. So these are, you can also, if you want to write, you can also express them in terms of the Fourier frequencies, but you know that here we have represented them in the space variables, and the space variables are the u and the v, which are the space variables at the output plane. And you know that zeta and eta naught is the coordinate of the point source located at the image plane. Here pi is actually the Fourier transform of p of xy in principle, is the Fourier transform of p of xy. So pi is also known as the Airy pattern. So you know that if we have a circular function, and if you take the Fourier transform of the circular function, what you get pi, you get Airy pattern as an output. So here we are using a Fourier transform of a p of xy, which is circular in shape, and if it is circular in shape, then you know that pi will be an Airy pattern. But you know that here pi, the circular Airy function also contains some phase dependent term. So this, you know that pi will be a complex Airy pattern, in the sense that it may contain some other information which may be present due to the addition of this phase factor, which is present with the pupil function p of xy. So thus the impulse response of the imaging system consisting of a single thin lens is proportional to the Fourier transform of the lens pupil function of the lens centered at u comma v given by. So here you can see that u is equal to, that is this capital pi is related with the image plane, and you know that the coordinates of the image plane are u and v, and you can here in equation number 4 you can find out those coordinates, that is u is equal to minus z2 over z1 into zeta, and v is equal to minus z2 over z1 into eta, by setting the arguments of the pi function equal to 0. So you can find out that this function, that capital pi, is resting on the uv plane at the output plane at these coordinates as given in equation number 74. So let's rewrite equation number 70 for a general point zeta and eta on the object. So look at equation number 70. So you see that here equation number 70 was written for particular points zeta naught prime and eta naught prime, which were the scaled coordinates associated with the point source located at the zeta naught and eta naught, which are shown on the left hand side in the kappa as the argument. Now you see that we want to replace zeta naught and eta naught with zeta and eta only, so that we can generalize the equation in number 70 for any general coordinate zeta and eta, which we have shown in equation number 75. So you see that in 75 you can see that we have replaced zeta naught with only zeta prime and eta naught with only zeta prime, and on the left hand side you can also see that zeta naught and eta naught have been replaced by their general values, more general values, by zeta and eta. Or you know that we can write it in the Fourier transform form as given in the second step in equation number 75. So kappa on the left hand side as a function of more general coordinates u and v, and more general coordinates zeta and eta, where the point source is present at the coordinates zeta and eta, any point source anywhere at any location of zeta and eta, and then you know that kappa will give you the image point field at the image plane as a coordinate u and v. So you see that that this is the full expression that we have given, and but here we have given the expression in terms of the Fourier transform of the lens phase dependent pupil function, which is p of xy into e to the power minus iota 2 pi zeta prime x plus eta prime y. So the curly brackets, we have taken the Fourier transform of the terms in the curly bracket. So using the value of kappa, u comma v and zeta naught and eta naught into equation number 60. Where is the equation number 60? So let's look at equation number 60. This is the equation number 60. You know that here we can substitute the values of kappa over here in equation number 66, and then we can find out the expression of the field at the image plane. So you know that kappa is also the field at the image plane, but kappa is the field due to a point source. If a point source is located at the input plane, that is at the zeta and eta plane, then the output field is kappa. But you know that if the input plane is not the field, is not the point source, but it is the field as shown in equation number 60, that is the field is u naught of zeta and eta, then the field will not, then the field at the output plane or at the image plane will be ui of u and v. So we are going to make a substitution kappa over here in equation number 60, so that we can calculate the output field. So here you see that we are going to make the substitution. So now we are writing the field on the left hand side. You can see that this is the field ui at the output plane, at the image plane, which as a function of u comma v, and then you know that these are the quantities we have already explained. And then of course we have plugged in the value of kappa in equation number 66, and this is the full expression for the intensity. But you know that here in the integral we have u naught, which is the field at the coordinates zeta and eta in the input plane. So u naught is the field which we have shown at the coordinates zeta and eta, and the corresponding to this input field we have calculated the output field at the coordinates u and v as a function of ui of u and v. So 76 gives you the complete description of the input field which we have given over here within the integral, and gives you the output field ui at the output plane as a function of two coordinates u and v as given in equation number 76. So one quadratic phase factor at the object plane lying within the integral, and the other at the image plane lying outside the integral. When measuring I of u comma v, then the quadratic phase factor at the image plane vanishes. So you see that there are two quadratic phase factors over here. One is the quadratic phase factor within the integral containing the terms zeta square and plus eta square, which is the quadratic phase factor related with the input plane, and the other is e to the power iota k over 2 z2 u square plus y square, which is the quadratic phase factor related to the output plane. So these two quadratic phase factors will vanish out from the integral when we consider the intensity expression. That is, we consider I of u comma v, that is we calculate the intensity expression from the equation number 76. So these two quadratic factors will vanish out from the expression. And you know that if ui of that is the output field at the uv coordinate is required, that is if we are talking about only the field at the image plane, the image plane quadratic phase factor is to be eliminated, and we want to eliminate the quadratic factor there. Then the field is measured on a spherical surface at the image plane. So in order to get rid of this quadratic phase factor, which is related to the image plane containing u square plus v square, if you want to get rid of this expression from the field expression given in equation number 76, what you need to do is that you need to measure this field where the field is measured on a spherical surface at the image plane having the center of curvature at the center of the lens and the radius equal to z2. So if you use such a spherical curvature at the image plane, then of course if you measure the data at a spherical surface, then you know that this ui will not contain the quadratic phase factor in u square plus v square. So this is the end of slide number 54.